All right, so let's talk about intermolecular forces, which is it contains one of the most frequently misunderstood ideas in chemistry. Intermolecular forces depend really on whether a molecule is polar or nonpolar. In other words, what type of intermolecular force and what strength of intermolecular force can operate between molecules depends on whether the molecules in question are polar or nonpolar molecules. And that means whether or not they have a molecular dipole moment. And we discussed in a previous video the difference between a bond dipole, and that just depends on electronegativity difference, and a molecular dipole, which of course is also going to depend on molecular geometry. So the three types of intermolecular forces that we're going to start with are London dispersion forces, dipole-dipole interactions, and hydrogen bonds, which are really essentially just an especially strong dipole-dipole interaction. And those are listed in increasing strength. So the weakest intermolecular force would be London dispersion forces. Dipole-dipole interactions are usually sort of an intermediate strength, and hydrogen bonds stronger than those. All of these are weaker than covalent or ionic bonds. Covalent and ionic bonds are intramolecular forces, even though ionic really isn't molecular. But it is important to note that these intermolecular forces are generally weaker than ionic bonds. And when we rank these in relative increasing strength, it's important to know that there are always exceptions to every rule. So there might be some dipole-dipole interactions which are weaker than other specific London dispersion forces in molecules, and we'll learn about the reasons why some dispersion forces might be especially strong or some dipole-dipole interactions might be especially weak. So when we talk about ranking these and increasing strength, that's a generalization, and occasionally there are exceptions. But we should be familiar with these three types of intermolecular force because we did study them before. And we had a foldable, if you took the course when we went through this way of introducing the material. I'll show you what it looked like. And if you still have this handy, then it might be a good thing to review. It's not especially important to find, but you might remember looking at this. We talked about the strongest intermolecular force, hydrogen bonding, and the intermediate and weakest intermolecular forces. But this information, if you don't have the foldable, is also going to be discussed in these slides. First of all, we'll start with dispersion forces. These are sometimes called London dispersion forces or London forces, and they're sometimes called van der Waals forces, although the term van der Waals forces can be used to describe all intermolecular forces in general, and so I'd avoid using the term van der Waals forces. In the AP curriculum, we're going to refer to these as London dispersion forces. The list of others appears here, but we're just going to focus on dispersion forces for just a moment and look at this animation that appears. You can see it's supposed to be an electron cloud, and it sort of looks like an egg that's a bit wonky as it kind of goes back and forth here. And really what that's trying to show is that the electron cloud, even in a nonpolar molecule, is a dynamic process. And there are going to be temporary fluctuations in the electron cloud, which lead to temporary dipoles. There's another animation you may remember that's shown here, which starts with two nonpolar molecules, N2. One of them has a temporary fluctuation, which induces a fluctuation in the adjacent molecule. And that's the basis for the intermolecular force called a London dispersion force. The electrons are dispersed around the electron cloud. Now, if one of them experiences this temporary dipole, which you can see this animation keeps cycling, but there's the temporary dipole in blue, it's going to cause a induced dipole shown in this red part of the animation on the right. And that's because the temporary dipole has a distribution of electrons which is skewed left. That's where the more electrons are, so there's a delta negative there. And that means there's a positive charge here. Well, that slightly positive charge is going to attract the electrons over here, causing another temporary dipole in this adjacent molecule. So for just a fleeting moment, there's going to be an attraction between that delta plus and the induced delta minus of this dipole. So that's the mechanism for London dispersion forces. And London dispersion forces are very weak because this is really just sort of a temporary phenomenon. They are caused by temporary, or also known as instantaneous, dipoles. So we're going to keep that phrase next to London dispersion forces because it's an important way to distinguish them from dipole-dipole interactions, which are due to permanent dipoles. It's not a temporary fluctuation in the electron cloud, but rather an electron cloud that is polar all the time. And you can see for just a moment when they're close to each other, the negative side of one is attracted to the positive side of the other, and that's the interaction we're talking about for just that moment. These dipole-dipole interactions can only act between polar molecules, molecules which have a permanent dipole. So let's take a look at the last type of intermolecular force called hydrogen bond. And the word bond is probably a bad word to use here, although we're stuck with it because that's the terminology that is accepted. A hydrogen bond is not a bond the way a covalent or ionic bond is. It's an intermolecular force. And it really is just a case of an especially strong dipole-dipole interaction, but it's really due to the fact that there are a couple of bond dipoles which, when they are present in a molecule, have some really extreme effects on interactions with other molecules. Those are the most polar bonds possible. They are N and H, O and H, and F and H. In other words, when hydrogen is bonded to N, O, or F. Now, why would that be? First of all, N, O, and F are the most electronegative elements on the periodic table. But hydrogen, remember, only has one valence electron. And so when it's bonded with N, O, or F, which are very electronegative, that electron cloud is going to be so concentrated on the NO or F end that hydrogen is left with almost no electron density, and there's an exposed nucleus of the hydrogen atom. So we call this hydrogen bonding. And this is a very important definition to understand clearly. It's very commonly misunderstood. Hydrogen bonding occurs when a hydrogen atom in one molecule, which is bonded to NO or F, is attracted to a lone pair on NO or F in another molecule. So the requirement is that we have hydrogen covalently bonded to either oxygen, nitrogen, or fluorine in a molecule. And the hydrogen bond is going to exist between hydrogen in one molecule and NO or F in another molecule. So water is often given as an example of hydrogen bonding, and it's a perfect example. Of course, lots of phenomena about water are due to this very strong intermolecular force operating. Its high boiling point, its viscosity, its high specific heat capacity. But it really is about the exposed nuclei of those hydrogen atoms. Remember, hydrogen only has one electron. And if it's sharing that one electron with very greedy oxygen, very electronegative oxygen, then there's not going to be very much electron density over here. So that exposed nucleus, that exposed proton, is going to be a partial positive charge, and it's going to be attracted to any electrons that are nearby, especially those in NO or F of an adjacent molecule. And that has some important consequences for water, like its boiling point, but also for other molecules which are capable of hydrogen bonding. And we'll talk more a little bit later about how physical properties like boiling point and melting point have to do with intermolecular forces. These are important questions for us to consider when we look at two molecules and are asked which is capable of forming stronger intermolecular forces. We want to think about the fact that if it is a nonpolar molecule, like nitrogen is, the only intermolecular force that can operate is a London dispersion force. If it is a polar molecule, then dipole-dipole interactions can operate, which are generally a stronger intermolecular force. And if it's a molecule in which hydrogen is bonded to NO or F, then hydrogen bonds can operate between molecules of that substance. And that's the strongest intermolecular force. So here, certainly we have water, which is going to exhibit the stronger intermolecular force. And it should make sense that at room temperature, water is a liquid, whereas nitrogen is a gas. The intermolecular forces between nitrogen molecules are so weak that It's a gas at just room temperature. Whereas in order for water to turn into a gas, we need really a high temperature to disrupt those intermolecular forces. Here's another example which compares two compounds, and we have in one case hydrogen bonded to NO or F, and in the other case hydrogen is not bonded to NO or F. So immediately we can make a determination as to which has the stronger intermolecular forces in each case. There are a couple other important things to consider here. One of them is the polarity of molecules. The one on the left is polar because it's an uneven distribution of electrons. There's some electrons on the right-hand side of the molecule around oxygen, but none on the left. So it's going to have a dipole moment. The one on the right may appear to be nonpolar, but it's important to notice that that central oxygen atom is a tetrahedral bent geometry. So that's an approximately 109.5 degree bond angle. So that actually does have a dipole moment. And dipole-dipole interactions can operate in this molecule. However, it doesn't change the fact that even though they're both polar, this one is capable of hydrogen bonding and this one is not. What does that mean in terms of boiling points? Well, the stronger the intermolecular force, then the higher the boiling point. Because in order to boil a substance or boil a liquid, then you need to overcome those intermolecular forces of attraction. So this is a good time to pause before we talk about some of the tricky pieces which are a little bit beyond what we learned in first year chemistry. However, questions like this, there's many of them which are worth practicing because they're a very commonly asked question on AP Chem tests. So there's a few tricky bits that we're going to talk about, specifically ones that pertain to London dispersion forces. So let's dive into some of the nuances here. It is important to note that London dispersion forces operate in all molecules, and it's sometimes a misconception that students have that London dispersion forces operate in nonpolar molecules but not in polar molecules, and that's not the case. London dispersion forces operate in all molecules. It's just that usually, if they're in a polar molecule, other intermolecular forces are going to be more significant, and London dispersion forces can be ignored. But all molecular substances are subject to some degree of dispersion forces, and that's because all electron clouds in molecules are dynamic, and they're going to experience some fluctuation. Usually stronger intermolecular forces exist in polar molecules, and the London dispersion forces become comparatively insignificant. Here's another tricky point about London dispersion forces, which should make sense. The larger the molecule is, the stronger the dispersion forces are. And that has to do with the polarizability of the electron cloud. The most common example we might consider is diatomic molecules like chlorine, bromine, and iodine. Now, chlorine is a relatively small molecule, whereas bromine and iodine are larger. Think about their electron clouds as like soap bubbles. If I blew a really small soap bubble, you'll notice those are usually a perfect sphere. There's not a lot of variation in the shape of the soap bubble. If you blow really, really large soap bubbles, ones that are like the size of a basketball, that would be akin to something like bromine or iodine. And there you'll notice that the soap bubble has a lot of variability to its shape. And that is what we would call the polarizability of the electron cloud. If there's a really large volume of the electron cloud, like there is for bromine or iodine, then the electron cloud is more polarizable. That means there's going to be more fluctuation in the electron density. There's going to be more temporary dipoles, and that means the intermolecular force that's operating here, the dispersion force, is going to be stronger. This actually explains why the state of chlorine at room temperature is a gas, bromine at room temperature is a liquid, and iodine is a solid, because iodine has such a large electron cloud, it's very highly polarizable, and there are very strong dispersion forces operating as a result. So it's not even a liquid at room temperature. And you remember seeing iodine vaporize, and that's because it doesn't take much to break those intermolecular forces. After all, London dispersion forces are weak, but a large molecule has stronger London dispersion forces. A final point that is stated here is that generally, if there's a molecule with lots of pi bonds, then there's going to be stronger dispersion forces. And this is due to the electrons in pi bonds being delocalized. If you remember the models we looked at for pi bonds, they are spread out both above and below the central axis of the sigma bond. And so that's going to lead to a greater degree of polarizability and fluctuation in the electron cloud. That means stronger London dispersion forces. So this is another transition point where we're going to move from learning about the intermolecular forces we learned about in first year chemistry and just reviewing those and taking them a little further to learning about some new intermolecular forces which are introduced in AP chemistry. The new material that we're going to be learning is something that the AP curriculum started emphasizing in the 2019 rewrite a little bit more, and that is dipole-induced dipole interactions and ion dipole interactions. And this slide explains that these are intermolecular forces that really only operate in a mixture. And I think it'll become clear why it would be a mixture that is always going to be the subject of these types of intermolecular force. So let's talk about them one at a time. The first we're going to consider is a mixture of oxygen and water. Now, if we consider just pure oxygen, O2, then the strongest intermolecular force of attraction that we would see operating there would be a London dispersion force. And what I mean by that is what intermolecular force would exist between one oxygen molecule and another oxygen molecule. Where O2 is a nonpolar molecule, that would just be dispersion forces. What about pure water? Well, hydrogen bonding only if it's between one water molecule and another. But what if we have a mixture of oxygen and water? And this is the case, of course, anytime we have water that has some dissolved oxygen in it. We are then going to see what we call dipole-induced dipole interactions. Water has a dipole. Oxygen does not have a permanent dipole, but a dipole can be induced in oxygen by water's permanent dipole. And here's an image which explains this. There's the isolated oxygen molecule, which is nonpolar. And here it is next to a water molecule, which is polar. Well, the water molecule's permanent dipole induces a temporary dipole in oxygen, and there is a weak, fleeting intermolecular force of attraction here called a dipole-induced dipole interaction. So this would only occur in a mixture of nonpolar molecules and polar molecules. But that happens quite a bit. For instance, if we have dissolved oxygen in water, or any other aqueous solution where the solute is a nonpolar molecule, often a gas. Now we're going to go on to the second new intermolecular force we'll learn about, which is called an ion dipole interaction. And ion dipole interactions, the title kind of explains it, is an interaction between an ion and a molecule with a permanent dipole. So is it an intermolecular force? I guess an ion is not really a molecule, so perhaps a bit of a misnomer, but we consider it, despite that, an intermolecular force. And this is an important one because it's how salt dissolves in water. There's an attraction between cations and water and anions in water. And essentially, when the ion dipole interactions overcome the ionic bonds, then solubility occurs. And if that doesn't happen, then we're talking about a substance which is insoluble or less soluble. Now, it really is an intermolecular force, and it doesn't fit cleanly into the definition of intermolecular force because ions aren't molecules, but it doesn't really fit into the definition of a chemical bond either. But an ion dipole interaction is a very important type of force of attraction we want to understand because it's so relevant to solubility of ionic compounds, which is an important topic in aqueous chemistry. So we want to model this and show how this is going to occur when you surround an ion in water molecules. And it should be clear that this is going to be the factor that really determines the solubility of ionic compounds. This is a Coulombic attraction. How far apart the ion is from the water molecule, or how the center of the ion is from the water molecule, is going to be a factor or a function of the size of the ion and also the charge of the ion. And so we're going to still want to think about Coulomb's law when we're thinking about these forces. Here's a nice summary of the types of intermolecular forces we've been discussing. And now we're going to go from the strongest down to the weakest. We've talked about ion-dipole interactions, like the kind that would occur between a sodium ion and water. We talked about hydrogen bonds, which are a very strong intermolecular force. We talked about dipole-dipole interactions, which are sort of an intermolecular force of intermediate strength. We talked about dipole-induced dipole interactions, and we've talked about London dispersion forces. You might see here also that there are ion-induced dipole interactions, and these are not included in the AP Chemistry course and exam description, but it doesn't take too much imagination to consider how these will operate. But we won't focus on those because they're not emphasized in our course curriculum. So finally, this summary of intermolecular forces does rank them from strongest to weakest. But as I mentioned before, for every rule there is an exception. So be careful about thinking too rigidly about whether one type of intermolecular force is always going to be stronger than another, because there are sometimes exceptions, and we need to evaluate each case on its merits and based on the experimental data that we collect. So that wraps up our discussion of intermolecular forces, and we'll do some practice problems that look at these concepts next.